The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
One quick erratum. The sodium fast reactor that I showed last time, I'll just show that slide again real quick. Where was it? Yeah. I think I had said this was a loop type. Whoever had said it's a pool type is actually correct. There are loop type sodium fast reactors, but whenever it's ready. This one is indeed a pool that just has some loops coming out of it. But I just wanted to make that clear. So whoever you were right. Before I start in with the process heat stuff, I just want to go over the group responsibilities. So some of you might be wondering, what are we responsible for overall, week by week? And I wanted to at least get you guys started with the first 2 weeks. So let me draw the crudest of plant layout diagrams. There's a loop here, and there could be a loop here. And there'll be some sort of heat exchanger, some turbine. Let's see. Have to continue this on the next board. Some heat. Hydrogen. Biofuels. Close. There. OK. So that's not going to fall off. So the core group, I'm going to have responsible for everything from the reactor, including whatever primary, tertiary, secondary loops you need, up to the turbine, including the hot side of the heat exchanger. So if I had to draw a border, the core folks would be responsible for this sort of stuff. The process heat folks would be responsible for designing the heat exchanger, whatever piping is required to get it to the hydrogen and biofuel plants, and any sort of heat storage, which I'll just draw in as a capacitor. You'll see a little bit why in the lecture. So this would be the process heat folks. So the three things you'll have to worry about are heat exchangers, heat transport, and heat storage if you choose to pursue it. And the hydrogen and biofuels folks are just worried about these circles up here. What goes in, what goes out. It's up to the process heat folks to tell you what the heat quality is going in. But then from there, it's up to you. So just to delineate. And if anyone has any questions about that, email me, see me at office hours, ask Tyrell. We'll be happy to explain more. Let's see. I just wanted to go over a little bit about what I'd like you guys to do next week. So as you probably guessed, since I've sent you like 1,000 emails already, I'm going to try to keep us pretty on schedule. So there are things week by week I'll expect you guys to do. And if you do them, we will be on schedule to have no work to do for the Thanksgiving break. So these next 3.5 weeks, I expect you guys to figure out what your options are, what are the pros and cons about them, figure out what's important, and decide the path that you want to go on. So starting on week 5, you'll be ready to go out and do some design. So for week 1, basically for next Wednesday, I'd expect you guys to be able to tell me what your options are. So for the core group, what reactor technologies are there? Which ones can you immediately eliminate because you simply can't use them? Let's say some folks are looking at liquid metals, some folks are looking at gas, some folks are looking at water reactors. Do you need secondary or tertiary loops? What's the coolant? What are the range of output temperatures? And I would do yourself a favor and find yourself 1 or 2 design papers for each type of reactor. So I'd say for the core group, if each person takes 2 or 3 of those reactor designs and becomes a 1-week expert on them, you guys will know what to do. So when you talk about what's important and which way you want to design, you'll be able to talk with each other and figure out, okay, I like this design, I don't like that design. For the process heat folks, I'll be talking about process heat all of today's lecture. Now that everyone's here, if you guys want to take a minute or 2 to sign the group contracts, I'll keep talking about the process heat stuff. So anyway, so the process heat folks, I'd like you to be able to tell me what sort of heat exchangers are there out there and what sort of size are you looking at to put in a reactor. What are some ways you can transport heat? What are some typical losses? Like, are you going to do it above ground? Are you going to do it underneath rock? And what methods do you have for heat storage? It's also going to be up to the process heat folks to really determine how far the reactor and the hydrogen and biofuel plants have to be. Because the further away it is, the harder your job is. So it's in your best interest to figure out what's the minimum distance those things have to be legal. And that'll help you minimize the losses from the reactor all the way up to the other board to the hydrogen and biofuel plants. For the hydrogen folks, I'd like you to be able to tell me what methods are there for creating hydrogen? What temperatures do they operate at? What are the efficiencies? At what lower temperature does the efficiency become negligible to the point where you wouldn't even want to consider it? What are your inputs and what are your outputs? Do you want to take in electricity? Do you want to take in heat? Is it something else? I don't know. That's for you guys to tell me. And for the biofuels folks, I'd like you to be able to tell me what biofuels are there? What sort of crops are grown? Or what sort of agricultural waste is taken to make biofuels? What are the inputs you need to turn switchgrass or corn or sugarcane into liquid fuel or gas fuel? What are the outputs? What are some of the byproducts that you might be able to repackage and sell as another product to improve profitability of the plant without any or very little extra work? So that's all I'll say. The next week, I'd say, is up to you guys to hit the books, hit the library, and the course book will be the internet. So I recommend relying on that heavily. Wikipedia, I might have said this, is not a primary source. Just so you guys know, you can use it to find primary sources. But primary sources would be things that would be published. Books, journal articles, conference proceedings, preferably peer-reviewed, technical documents, things like that. But you're welcome to use it to find primary sources. Let's see. I'll just say a little bit about week 2. So when we come back next Wednesday, we do have class Monday, I should say, but when we meet next Wednesday, you guys should know what your options are. Over the next week, you'll be able to start defining what are your criteria for success? What's your goal in designing this plant? Do you want to make more electricity or more biofuels or more hydrogen? What are some of the importance metrics? How do you decide importance to certain parameters like output temperature, how much heat losses? What are your hard and your soft constraints? And there'll be a lecture about that next week. So you don't have to really worry about that yet, but do keep in mind, as you're coming up with these designs and hitting the books to find out what's out there, what would you consider to be the most important aspects of each of these technologies? And what are some sort of ancillary concerns that you might have down the road? So with that, has everyone signed the group contracts? There's 3? Okay. Who are we missing? Okay. I don't know where the core leader is either. Okay. Well, whenever he gets here, oh, nice. Signed, dated. Good job, guys. They get the filthy handprint of approval. It's from carrying this heat exchanger over. Why don't we start out with the process heat stuff? Let's make sure that's working. So this will be about the process heat group. I don't know if I've mentioned before, the reason I'm getting into specifics for every group with you all here is I want to make sure you all have some common ground, so you'll know what to expect from every group. You don't necessarily have to be an expert in it, that's their job, but you'll all have some common ground with which to talk about your design parameters. So the 3 main challenge problems for this process heat group are heat exchangers, heat transport, and heat storage if necessary. It'll be up to you guys to decide whether or not you want to have heat storage. So to start off, some nomenclature. Some of these terms confused me because it turns out I didn't think I know what they meant until I read them and I realized, wait a minute, I know this stuff. This is sort of a more mechy flavor on terms. Have you guys heard of sensible heat before? A couple yeses. So sensible heat is just a temperature change, the old Q equals mCp delta T. Latent heating is a phase change. So the amount of heat put in is dependent on the heat of vaporization or the heat of melting, boiling, freezing, whatever. And there's also some bond energy storage, which is what I say, you store energy in a chemical reaction. So you can run a chemical reaction in one way or the other and add or remove heat accordingly. So where do we find heat exchangers? I just put up the old gas fast reactor. Where are the heat exchangers in this plant? Anyone just shout them out? Okay, so anytime you see something like this, where you have one fluid bathing another one with a whole bunch of coils and things, that would be your heat exchanger. So there's it's hard to read on the screen just because of the resolution, but for those of you with handouts, these say heat sink. So these two here, this pre-cooler and this intercooler, are heat exchangers. This recuperator's heat exchanger. You're also going to need a heat exchanger to pass off the heat from this piping to the hydrogen and the biofuel plants. Actually, let me do this just so it's a little easier to see. So some fundamental parameters of heat exchangers. One of them is the effectiveness, not the efficiency, but the effectiveness. It measures how much heat is transferred compared to how much is possible. So can one fluid absorb all the heat from the other fluid? If it's so, then the heat exchanger's effectiveness would be 1. This is just sort of a diagram showing temperature and length through the heat exchanger for the hot leg and the cold leg of the heat exchanger. The solid lines show what a more typical heat exchanger would look like, while the dotted lines show an effectiveness of one heat exchanger. Now you'd think you'd want to be able to get all the heat out from the hot leg into the cold leg, but can anyone tell me why that might be a bad idea? No? That's okay. Don't expect you to know at this rate anyway. So at any given point in this heat exchanger, the temperature difference determines the potential for heat transfer. So even over on the solid line, even over here, there's a sizable temperature difference for transferring heat. As you go down the heat exchanger, this potential gets less and less and less, and the heat exchanger gets bigger and bigger and bigger. So at some point, there's going to be a trade-off between how much more heat can you pull out of the hot fluid into the cold one, and how much bigger do you have to make this heat exchanger? So there is a trade-off there. Just to show you a little bit of the cross-section of a heat exchanger, basically it's just two fluids separated by a wall that's hopefully thermally conductive. There are thermal resistances in the wall. There's the convection through the fluid. There can also be some junk building up on the wall, known as fouling. And I brought in an example to show you guys, a couple examples of heat exchangers. One would be a clean one. Does anyone recognize this from chemistry? Condenser. If you just want to pass that around, you can sort of see how the cooling fluid would flow along the outside, and whatever you want to cool down, your hot fluid would be flowing on the inside. The old, the Prohibition-era moonshine stills, other examples of heat exchangers. All you do is you have some hot ethanol vapor that you want to cool into a liquid. They're everywhere. Here is a more serious heat exchanger. It's disgusting, so I won't pass around the end plates. But I just wanted to show you guys sort of what's possible. This thing right here can transfer 2,500 BTU per horsepower per hour. And since I know you guys don't know how many hogsheads are in a furlong or any of those other imperial units, this can put out about 30 kilowatts for a 40 horsepower motor, which is what we connect it to. It is a 4-pass heat exchanger. So the fluid comes in and actually makes 4 passes through the fluid. You can see that there's some lines right here, some plates that separate out the fluid. The end plates have similar caps on them, so it actually ends up passing through 1, then on the bottom 2, 3, 4 times. And this is what's called a shell and tube heat exchanger because there are tubes inside the shell. There are many, many, many tubes. And this is a perfect example of fouling. So I don't know if you want to pass this around or if you want to come up and look at it later, but whatever you guys want to do, you're welcome to it. And it's pretty disgusting. That's why it's here and not cooling our hydraulic systems back in the lab. So whenever you are designing your heat exchanger, I'd like you guys to think about what fluids, what working fluid are you putting in? Is there a possibility for fouling? You have to think about not only the materials concerns of the fluid in the reactor, but in the heat exchanger. And the design of the heat exchanger is up to the process heat folks. So the core folks will have to tell the process heat folks what their primary coolant is. And it's up to the process heat folks to pick a suitable secondary coolant so as not to corrode in the heat exchanger. So one of the fundamental equations for heat exchangers is this deceptively simple one up here. Looks kind of like, you guys ever heard of Drake's formula? That formula for whether or not there's extraterrestrial life? It's just like 50 numbers multiplied by each other. This one looks simpler, but it can be more complicated. Q is the heat transfer rate. So in the case of that filthy thing is 30 kilowatts. U is the thermal conductance, which is the inverse of the thermal resistance. A is the heat transfer area, or the effective heat transfer area. F stands for factor. All of that depends on flow configuration and all sorts of other parameters, and I'll talk a little bit about how to find that. And delta TLM is the log mean temperature difference, which is a good indicator of how good a heat exchanger is at getting the heat out, depending on which kind of flow. So here's the formula for log mean temperature difference. So this is the change in the hot leg temperature, the change in the cold leg temperature. Oftentimes, if you have two heat exchangers of the same size and they have different configurations, you'll notice the log mean temperature difference is different. Bigger log mean temperature difference usually means it's better at getting heat out. And I'll tell you, counterflow, which is when the fluids flow at opposite directions, tends to be better than parallel flow when the fluids flow in the same direction. This is how you tend to find parameters for a heat exchanger. You get a book of big complicated charts, and you look up a number on a big complicated chart. You don't need to read the axes here because they're not important. This is what I would expect you guys to be finding. For whatever geometry heat exchanger you find, and for whatever coolant and whatever effective area, whatever, you'll be able to find a chart. Lots of people have spent lots of time compiling lots of charts to find the parameters in these things. Some of the fundamental other parameters for heat exchangers, like I said up here, is the effectiveness of the heat exchanger. These C's right here, C just stands for mass flow times heat capacity, m dot times Cp. It's called a capacity rate. And C star will give you an indication of how balanced the heat exchanger is. Can one fluid give or take all of the heat from another fluid? C star is just a ratio between the minimum and the maximum capacity rate. One is for one fluid, one's for the other. If C star equals 1, it means that one fluid can give up its heat just as fast as the other can take it. If not, then you could be wasting some heat. And NTU stands for number of transfer units. If you notice, the thermal conductance times the area over the minimum capacity rate will give you the number of thermal units. It's just sort of a way to non-dimensionalize the heat exchanger. Could anyone tell me why you'd use C min instead of C max in this formula? Or is anybody lost at this point? It certainly is. The limiting factor is the fluid that can take or give heat the slowest. So that's why we use C min on the bottom here. And a quick way to gauge the parameters of a heat exchanger is to find as many of these fundamental parameters as possible. And there are methods like the NTU method, where if you have some of these parameters, you can look at a big complicated chart and usually find the other one with some degree of accuracy. There are lots of flow types. There could be a single pass heat exchanger like that chemistry condenser I'm passing around where the fluid only goes through once. There can be multi-pass ones like this monster right here where it actually flows through 4 times. Let's see. As I said, there's counterflow and parallel flow. Does everyone understand the difference between those? If not, just raise your hand. Okay, good. There's also cross-flow, where the fluids flow perpendicular to each other. And there's pluses and minuses based on plant layout and what you want to get done for each of these. So like I said, it'll be up to the process heat folks to determine which one of these you want to go with. And there's lots of other subgenres, but once you sort of get yourself down to this level in this chart, you'll have a good idea of where you're going. Just to show you some temperature versus length diagrams for parallel flow versus counterflow. In this one, the fluids are flowing in the same direction. And one fluid can never get hotter than the other one can get cold. The best thing they can do is meet somewhere in the middle. It might not be exactly in the middle if the fluids have different capacity rates, that m dot times Cp, but it's going to be close. Whereas in counterflow, the hot fluid can really warm up the cold fluid beyond the temperature of where the hot fluids ends up at the end. As for flow configurations, there are tubular heat exchangers, like the 2 that I brought in here. There's plate type, spiral, printed circuit, all sorts of crazy things. They all have their pluses and minuses. The nice things about things like tubular heat exchangers is they offer nice cylindrical flow channels. They're a fairly low pressure drop unless your tubes get really, really thin. They are getting kind of thin here, but there's a 40 horsepower motor behind the fluid there, so it's not so bad. Something like a printed circuit heat exchanger is very good at getting heat out, but it also ends up with a much bigger pressure drop for the same power rating. The one we have in lab is bigger than this table, so I decided not to bring it in to show you guys. And there's all sorts of other ones. Just a few diagrams to show you what some of these things look like. This is actually fairly close to what we have right here, except it's a 4-pass, and I don't actually know if there are any of these what's called baffles here. That's just to cause the fluid to flow over all the tubes, mix a little bit better. And this one should look fairly familiar. I don't know who has it now, but that's pretty much what we've got there. There's a plate type heat exchanger where fluid flows through a series of tubes and then passes over plates. And the nice thing is those plates have a nice surface area, and it's a fairly large surface area. There's a spiral type heat exchanger where the 2 fluids flow either in the same direction or in the opposite direction around a spiral. If anyone has ever seen you know those little electrolytic capacitors, like the little soda can caps? Does anyone not know what I'm talking about? Okay. There are some devices called capacitors for storing charge. A capacitor is just 2 parallel plates. If they were actually 2 straight parallel plates, it could be pretty big. So what they tend to do to make electronic components small enough is you wrap the plates around each other into a little tube, and you end up with this little can-looking thing that's much more compact. And this is a good example of where it can land you in heat exchanger land. So there's actually a lot of analogs between electrical systems and thermal systems, and I'll get into a little bit of that in a sec. As far as heat transfer mechanisms, this is what phases is the coolant in, and what heat transfer mechanisms, convection, conduction, radiation, are you dealing with? Is it single phase on both sides? So what would it be? What would an example of a 2-sided single phase heat exchanger be? Air to air, water to water, liquid sodium to mercury. Something where everything's in single phase, and it's all, what kind of heating is that? Sensible. Yep. It could be single phase on one side, 2 phase on the other. Where do you find these sorts of heat exchangers in a nuclear plant? So if you think about it, single phase on one side, 2 phase on the other. Steam generator. Yeah. So like a steam generator in a liquid lead plant or a sodium plant, you have only liquid on one side, you have liquid and gas on the other. And when you evaporate the gas, what's that type of heating called? Latent heating, yep. You could have 2-phase convection on both sides, so you could have boiling on one, boiling on the other. I would not recommend freezing because then you would freeze the coolant in the tubes and stop flow. You could have combined convection and radiative heat transfer. I doubt you guys are going to do this because it would have to be glowing, at least in infrared, if not red, orange, yellow, white, hot, whatever. So to summarize, the main questions that the process heat group should be asking itself is, what type of heat exchanger do we use? And before you get baffled and think there's 1,000 types of heat exchangers, try and find out what people use in existing power plants and other paper reactor designs. So this would be the time to hit Journal of Nuclear Technology or Nuclear Engineering and Design and see if you can find what other folks have done as a starting point. What are the working fluids? You're in charge of some of them, and some of them will be dictated to you. So the core folks are going to tell you, this is the working fluid we've chosen for our core. And you're going to have to deal with that and choose your other working fluid for the other side of the heat exchanger. What geometry? Do you have to worry about flow? So you can make a great heat exchanger with thousands of tiny little tubes, but you're going to lose a lot of pressure pumping the fluid through those tubes. Is it going to be laminar or turbulent flow? And just raise your hands, does anyone not know laminar or turbulent by now? So you've all taken 2005? Okay, good. Where's the trade-off between cost and performance? Do you guys want to go with a heat exchanger with an effectiveness of 1, or do you want to be able to pay for it, is the real question. And are there materials concerns? So you have to think about what the coolants could be doing in terms of corrosion in the heat exchanger. Could the coolants have things dissolved in them that when they cool down in the heat exchanger, just like this one, they foul it up with deposits, just like this one? What happens when the heat exchanger gets too hot? So what if there's a transient? Will the tube start to soften? If you use, let's say, a ferritic martensitic steel, will it undergo a phase change and turn from something nice and strong into butter? Just wondering, has any of you guys taken the blacksmithing class here over IAP? Or done any sort of metal work where you actually get things red hot? You have? Yeah. What'd you done?
It was just like the stupid thing. And we just like heat up these like huge metal rods and get piston.
Well, that's precisely what I was hoping you'd see. So there's a certain temperature. You know, you can heat up a bar of iron to about red hot, and you still cannot bend it. And it gets beyond a certain temperature, the phase transformation temperature, when it goes from ferrite or perlite or whatever to austenite, and you can just bend it. Like, it'll even bend under its own weight. And then as soon as it cools down enough, the thing just stops. You want to make sure that doesn't happen in your heat exchanger tubes. So think about the materials, not just from a corrosion point of view, but from a dissolved species point of view, from a phase stability point of view, from an aging point of view. There you go. Another thing, if you have dissolved products in your coolant and they're radioactive from the core and they foul up in the heat exchanger, what does that mean for the dose, for the workers? What do they do if they have to replace a heat exchanger and it's full of radioactive crud? So keep these things in mind. I don't expect you to know them in and out until the end of this design, but it's good. Yeah?
Would that change the resulting rod in any way? Like, would it make it more brittle or anything like that?
You mean the crud deposits?
Yeah, well, whenever you bend the rod, you said like you heat it up a lot.
Mm-hmm.
So when it bends, does it actually change the material property of it at all? Like, is it more brittle?
That depends on what temperature it's at. I will be doing materials a little later, but I can just tell you now, if you have a piece of steel, which at room temperature is normally ferrite or perlite or martensite, some sort of harder phase. If you bend it and it doesn't bend back, you've plastically deformed it, and you can do what's called work hardening. Have any of you guys ever taken a piece of copper wire and bent it a couple times and it just snaps apart? The same sort of thing happens in steel, except you have to bend it more. If you heat it up to the point where it transforms from a body-centered cubic crystal structure to face-centered cubic, from ferrite to austenite, you can just sort of deform it like this. It's got more slip systems, more ways to deform, and it's hotter. And depending on how fast you cool it down and what temperature it was at, you can cause some permanent damage to the metal or not. You can also remove some of that damage by heating it up a lot more, which is called annealing, and cooling it down slowly enough so that you don't quench it. Man, maybe I should get you guys in the forge one of these days and do a quench and temper demo. I'm going to think about that. Have any of you guys been down there? Or, yeah?
I was just going to say you have a couple references there. Another really good one is a book by Hewitt that's also the heat exchange
Oh, yeah?
handbook.
Could you mail that out to the class, actually?
I'll
If you
send
get the
it.
reference?
Yeah, I'll send the reference. It's about like 3,000 pages long. It's in 2 or 3 books, and he does a very good job of outlining how to solve problems with it, and like how to use it. So
That's great. Yeah, I put up a couple of these references because I think the heat exchanger will be sort of the most confounding and thermodynamically difficult part of this design. So give you a little head start. And yeah, if you could email out that reference, that would be great. Thanks. So on to heat transport. The main problem is getting the heat from the reactor all the way to the top of the other board for the hydrogen and biofuels plants. What are some things that can happen during then? I mean, it doesn't, unless you are able to transfer the heat without any temperature loss, without any pressure loss, what could happen? I mean, you could have some losses somewhere, right? There'll be some temperature losses. There could be some pressure losses. These are the things you guys got to think about. So you've got to consider what temperature is the core group giving you heat at, and so what temperature can the heat come out of the heat exchanger? By the time it reaches the processing plants, what temperature is your working fluid now? What temperature is it when it's coming back? Is it too cold? Is it too hot? Is it just right? What are the flow rates, and what are the implications? If you jack up the flow rate, does the pressure drop go up? Does it become harder and harder to pump things? And what happens during transients? So if all of a sudden the cooling fluid heats up a little bit, do you have any materials concerns or concerns that'll propagate down the line and affect any of these other groups? There's also, how do you want to model it? Like I said, thermal systems can be modeled as electrical systems with resistances, with capacitances, which I'll get into in a little bit. Do you want to model it as a finite element system? So let's say you have a pipe transporting hot steam or something underneath bedrock. Do you want to model it as a series of resistors? Would you want to model it using a finite element mesh so you can actually visualize what the temperature is and give different parts of the rock different properties? Do you want to do loop analysis like pencil and paper analysis like in 2005? How do you pump it? Is it going to be forced? Is there a way you can site this system of plants so that it could be gravity fed? Is it possible? Because if so, you could save a lot of pumping power and cost in the pump. And like I said, you guys are in charge of figuring out the distance from the reactor to the hydrogen and biofuel plant. So the more you can figure out exactly how close you can put those things, the easier your life is going to be. So the main questions I would ask myself are, what are the constraints? What's the heat coming out of the reactor? What are the temperatures that the hydrogen and biofuels people need to produce their products? And if you can't get them, do they have to change their methods or do they have to change their outputs? So there's going to be a lot of back and forth and iteration, back and forth along the line between all of the groups. Where if the biofuels folks, or let's say the hydrogen folks say, I want to do the sulfur iodine process. I need heat at 800 Celsius. Can you even deliver that? So there'll probably be some arguing between the groups. And there'll be plenty of time in class to duke it out as the semester goes on. How far does the heat have to go? Where do you take the heat from? I drew the heat exchanger above the turbine. It doesn't necessarily have to be there. It could be below the turbine. You could split the flow if you wanted to, depending on how much heat and what quality or temperature of heat you want to deliver. How do you transport it? Like I said, is it forced? Is it going to be pumped? Is it gravity fed? How do you model it? Think about what are the losses, and should some of it be stored? Which brings me to the last challenge problem for the process heat folks, is heat storage. Heat storage is a nice way to add a capacitive effect to your thermal loop and balance out some temporary instabilities. Now this could be anywhere. Your heat storage could store anything from kilowatt hours, which would not be very useful, to megawatt hours to gigawatt hours, to the point where you could start running the full load of a plant for 15 hours. Of course, there are size and scale and cost implications for having a gigawatt hour thermal storage system, but I think you guys will be able to figure it out. You can store some heat to run the turbines or the product factories during transients. or during any other thing that could happen. You can help or avoid or delay plants from load dumping or load following. Does any of you guys know what load dumping or load following is? Just raise your hand if you do. OK. Load dumping. If I were to use another board, let's say I want to graph the available electricity versus the demand over the cycle of a day. So here is 12 o'clock. Let's say here's 12 o'clock. Here's 12 o'clock. Here's, 6 o'clock, 6 o'clock. Over the course of a day, the electricity demand is going to peak during business hours and then come back down. Now, let's say for some reason there's a grid failure here, and you lose that much demand, yet your available baseline power delivery is like this. Power plants don't take kindly to their load being shut off. And so as a result, you might have to dump some of the load. You just dump the heat into a cooling fluid and let it go off in order to keep the plant running at a steady level. Or let's say that there are some instabilities in the grid, or you want the plant to be able to change its power level as the demand changes. I don't think too many plants in the US do it. I know the plants in France do, because I just saw a pretty cool graph of if you looked at the power level versus fuel cycle, the US one looked something like this, where there was a partial shutdown, there was an unplanned outage, and then it went off. And the French one looked like this. So they try their best to follow the load demand. Now, having heat storage can help smooth out some of the shorter-term instabilities if you decide to design it right. And it's up to you to decide, do you want that or not? So here's an electrical analogy to a thermal system with heat storage. The battery over here would be the reactor. This is your source of power. And you would like for that reactor to either be on or off. You don't want to start changing resistances. You can switch on or off this source. So let's say you lose connection to the grid. That would be like switching it off. Your resistor is the whole combination of your load and your losses due to transport, dissipative, hydraulic losses, transformer losses, whatever. And the heat storage system acts like a capacitor. So let's say you're starting cold, and your reactor starts to heat up and start passing some power, which here is modeled as current, through this loop. Maybe for the first 10 hours, you don't start running the turbines. You start heating up your heat storage system so that if something goes wrong for a little while, you can flip this switch and have your heat storage system continue to provide power to your load and your losses. So it's up to you guys whether you want to do that or not. And there are benefits to it. There are costs to it, like the cost of building the system. Like I said before, there are 3 technologies. You can use any combination of sensible heat storage, which is just heat something up and then let it cool down. There's latent heat storage, where you can melt or boil something. I would recommend melt, because if you boil it, there's going to be a pretty big density change. And bond energy storage, which I'll get to a little bit. For bond energy storage, I don't know if I've mentioned, you'd want your reaction to be reversible so that there's no irreversible losses in that bond energy storage system. An example of a sensible heat system is pretty simple. Just some spheres of a material, here it's alumina, with a hot gas going through them. So when the reactor is on, it's sending its hot working fluid through this tube over these spheres, and these spheres heat up. And eventually, when it reaches equilibrium, the spheres are roughly the same temperature as the working fluid. So let's say this working fluid is shut off. You can have a pump continue to pump cold fluid through. By the time it gets out, it's hot again. So in this way, you're just heating up and cooling down these little spheres of alumina. You'd certainly want to insulate it thermally, because otherwise you just lose all your heat. Other examples of sensible heat, pipes in concrete. You can just have a giant block of concrete and run some pipes through it and heat up the block or cool down the block. And this is actually a test block from the University of Stuttgart Center You can also have what's called a thermocline system, where you have hot molten salt, cold molten salt. It'll separate naturally as long as the thermal conductivity isn't too high. For places to look for good heat storage examples, look to the world of solar. I know by your shirts, at least the two of you, plus the one that I wore last time, we might not be the biggest fans of solar, but they have some good ideas. Because they know that solar energy only works when it's light out. So there's no way people can accept solar as a baseline source of power unless you can store extra during the day and release it at night. So I would say look to some solar books and conferences, especially the recent conferences, if you want to get some good examples of heat storage systems. As far as phase change materials, all sorts of compounds melt at all sorts of different temperatures, all the way from water up to molten salt, which melt at something like 800 or 900 Celsius. So there are materials out there for whatever you need. You need to look at things like the thermal conductivity, the heat capacity, the heat of fusion, and that'll be able to tell you how much heat can you store in them and how quickly. I would also look and see if there's a density change between the solid and the liquid system to know whether you want to have a nice hard sealed vessel or you want to give it room to expand. There are some problems with the higher temperature heat storage systems. For example, molten salts can be corrosive. You're not going to be forming tritium like in a reactor, but molten salts on their own, especially things like chlorides or whatnot, can be fairly corrosive. Some ways that they've used to improve heat transfer in these latent heat systems is to run graphite foil through them. Since graphite's pretty thermally conductive, it's a good way to spread heat throughout the whole system. So instead of just having a big tank of solid salt that becomes molten salt, you may want to have layers of graphite to spread the heat out, get it there quicker, and then you can model the entire thing as a lumped parameter, a constant heat system, if you do it right. And then as far as bond energy, you can run a chemical reaction in one direction or the other. If you change the temperature or the pressure, you can cause the products to become reactants or vice versa. And if it's exothermic in one direction, you can get heat back out of it. Some examples would be hydration reactions. There are reactions that either heat up or cool down when it forms a hydrate. You can do hydriting. For example, I think someone is using a magnesium hydride system where you actually use hydrogen as energy storage. So when the hydrogen combines with magnesium, it either gains or releases energy, and you can run that reaction in reverse and run the heat engine in reverse. And there are ammonia salt reactions, which are better for some higher temperature ones. So I would look there. And like I said, the chemical reaction should be reversible. So the main questions for heat storage is what temperatures are required. So you may want to look at, once you design your whole process heat system, where in that system would you want to put a heat storage system? Is it going to be at the hottest part or the coldest part? That'll help you determine which one of these salts to use for latent heat, or how big to make your sensible heat system, or which chemical reaction to pick for a bond energy storage system. What materials do you want to use? What capacity do you want? If you had sorry, that should be a capital M, not a milliwatt hour. It's not very useful. If you had a megawatt hour system, how useful is that? I mean, in a power plant, how long would that last you? Minute, less than a minute. If you have a 1,000 megawatt plant with a 1 megawatt hour capacity system, you're talking about seconds. But still, it's up to you guys to size it. It's up to you guys to choose whether you use it at all. How does cost scale with size? So for example, if you have a megawatt hour tank of molten salt versus a gigawatt hour tank of molten salt, how much more does it cost to increase your storage capacity by a factor of 1,000? Do you start getting diminishing returns, or does the cost sort of plateau to the point where you can say, beyond here, it doesn't even matter what the cost is, it stays pretty much the same? What are the loss rates and pathways? So you have to figure out where heat could get out, both in terms of where it'll do so in steady state, as well as in an accident scenario. What if some salt starts to leak out? When would it be used, if at all? And where would it be located? Both in your design schematic and physically. Would it be located closer to the hydrogen site? Would it be located on site at the reactor? And that depends. Do you want to make sure you can make hydrogen during an outage? Or do you want to run the turbine a little more? Or do you want to let it coast down? Up to you guys. And that's pretty much what I have for the process heat, folks. So Brendan, do you have the core contract, the group contract? Has everybody signed it?
No, we're going to sign it in the class.
Okay, well you guys can just do so right now. In the last 5 minutes, I wanted to ask you guys, do you have any questions about what I expect from you guys for week 1? Or beyond, or further on, do you have any questions about the course at all? Nothing. So you guys know what to do. That's good. Well, I'll also just add, I mentioned this to the focus area leaders and the integrators. If there's anything in this course that you don't think is going right, I'd like you guys to tell me, because I know while I'm the instructor and I get to determine your grade, you guys get to determine a big part of my future with your evaluations at the end of the course. So I'd like to make sure that everything is going as you think it should. You know, beyond things like can we all get A's, I'd like to know if you think there's a better way to run the design problem. And if you guys have any ideas, by all means voice them. After all, it's your design. So you can feel free to contact me or Tyrell or talk to your focus area leader if you're not comfortable for some reason, and they can relay it up the chain, stay anonymous, whatever. It's all up to you guys. So let's see. Does every group have an established time for them to meet each week? Not yet? Okay. I'd say in these last 2 or 3 minutes, the groups that don't have a meeting time in place, figure that out now, because pretty soon you guys are going to have to meet to decide how to split up the work, what to look for. So who gets to decide, you know, for the core people, who's going to look at what core concepts? Who's going to look at the turbine? For the process heat folks, who's going to do heat exchangers? Who's going to do storage? Who's going to do transport? For hydrogen, split up the concepts and pick who gets to do who. For the biofuels, who wants to do inputs and outputs? Who wants to figure out what production methods are out there? I say you guys can do that right now.